Africa since many years. And so you will see, I will take you on a ride through forcings of rainfall, through climate forcings and climate change in Southern Africa. I know you are non-meteorologists, so I try to be, relatively easy on a high aggregated level, but I also encourage you to, go with me on that journey through the climate in Southern Africa. Okay, so I need to, yeah. So I start with a map, mean rainfall in Southern Africa. Of course, for rain-fed agriculture, rainfall is very important. And I hope you can see my cursor. I make a laser pointer here. You see Southern Africa. So when I talk about Southern Africa in this talk, I mean the region here is, including Angola, Zambia, Mozambique here, but not Congo and Tanzania. So this region here, the southern part of Africa, is covered by my class. And we see, of course, the strong here gradient in rainfall here in southern Angola and Zambia here, the very dry parts of Namibia and South Africa with the very, very dry Namib Desert, and arid Botswana, and the aridity is stretching a little bit here across southern Zimbabwe to southern Mozambique. When we look into the rainy season in most parts of southern Africa, except here, the southernmost tip here, the Western Cape region, where the rain are occurring through austral winter. Most of the rainfall is in austral summer, as you know. When I say austral summer in my class, I'm referring to months like November through to April here. So you see, of course, the monthly rainfall after paper by Hull et al. The rains start in Angola already in northern Zambia in November. There's a little bit of rain also here in northeastern Republic of South Africa. And then, of course, the rainy season sets in. February, for example, could be considered somewhat of a peak of a rainy season here. And then the rains start to retreat in March and April. So I'm not covering most of the time Madagascar. I'm covering this part, as I mentioned before. So what are the factors responsible for natural climate variability and change? That is very important. When you discuss climate change, anthropogenic climate change, you need to understand the climate system. And I'm referring mostly to factors that were responsible for variations in rainfall. I start with these two maps here. So these maps are at 850 hectopascals. That is usually about 1.5 kilometer above mean sea level. Here you see the situation between here. That is April, May, June, July, August, September, October. So that's our austral winter. And that is the situation in November, December, January, February, March. This is austral summer. So let's start with austral summer, where I said we have a rainy season in most parts of southern Africa. And what you see here is as contours the height of the 850 hectopascal level. So if you have larger values, you have a high pressure system at that level, also at the surface here. For example, here we have the St. Helena high pressure system, that the St. Helena anticyclone, as we say, that here numbers mean it's 1,548 meters about that above ground. We have here at the eastern edge the Mascarene anticyclone here, And in also summer, we have low pressure systems. One is over the ocean, the Mozambique Channel Trough, often abbreviated MCT. We have the Angola low over the highlands of Angola, and we have the Kalahari heat low. I'm coming to that later on. Then you see some black arrows here, and they indicate the flux of moisture. The moisture feeds the rain over the region here into southern Africa. And one source is here from the northeasterlies. They are part of the Indian monsoon system here. And this is here a flux from south of the Mozambique Channel. So I can already tell you that the bulk of the moisture for the rains are coming from evaporation from the warm Indian Ocean. There's a little bit of moisture coming here in northwestern Angola from the Atlantic. And if any, here it's very dry, some moisture coming here from this part of the Atlantic. What you also see here, and I'm coming to this later on, is here it's called Zambezi low-level jet, Limpopo low-level jet. So these are two big river valleys, as you know. And through these valleys, there are jet streams at low levels, especially at night. And they are actually responsible for the bulk of the moisture that enters here, the high plateaus here of Angola, also Botswana and Namibia. So moisture is coming from the Indian Ocean. It's transported onto the continent here through these valleys here. And of course, what makes it raining here, I come to later. Then we have the situation during the dry season. Basically, you see here the St. Helena high has shifted northward here. There are no Angola lows, Mozambique Channel, and heat low in Austral winter. There are still these jets, but they, transport moisture, but the moisture is not used in a lot of rainfall over the continent. So now I'm sorry here. I need to make a correction here. There's something wrong, which I want to, yeah, okay. Give me a minute here to correct that. That should not have happened. I'm sorry about that. I tried to share again and hopefully it's going well. Yeah. Okay. So I hope you can see the slides now. If not, please indicate it to me. So this is a very noisy slide from Despiol et al. So I just want to, highlight a few things that we have already seen before. It's again the situation during Austral summer. And you see here, let me get to the laser pointer. You see here the outlines of Southern Africa. You see in green arrow this time the incoming moisture flux. So here you can already see by the width of this arrows how important it is. So from these northeasterlies here, a lot of moisture is coming to the continent. Yes.
Please, may you please put in the presentation point, because they say they can't see when you are pointing.
Can you just can you go closer, please, to the mic? I didn't get you. Can you say it again, please?
Yes, sorry. May you please put in the PowerPoint presentation mode?
Okay, I'm sorry, I have the presentation mode here. So let me go back and try to start again. I'm sorry. So thank you for making me aware of it. So I'm just trying to, yeah. Okay, hopefully it's working again. So, Can you see the presentation mode now?
Yes, you can see now.
Okay. Okay, I'm sorry about that. Yeah. Okay. So you see here the moisture, as I said, coming from the warm Indian Ocean. There is a little bit of moisture coming from here, the Atlantic Ocean for northwestern Angola. Here is the Angola low rotating this way, but I wanted to make you aware of these diagonal cloud bands that occur over southern Africa. They are associated with so-called tropical temperate troughs. I will show you that in the next slide. So this is a feature whereby moisture from the tropics, can flow here southeastward. And it's really very important for the rains in the eastern part of the Republic of South Africa and also in Botswana. Okay, here is some, work from famous synoptic meteorologist von Herden and Taljaard here. And you see here a sketch of South Africa here. You see here the intertropical convergence zone that is called, I'm going to the, laser pointer again, the interocean convergence zone by them. You see here the rains in the tropics, and there's a cloud band here on day one, and on the next day, this cloud band is connected to the mid-latitudes. You see here a frontal system. And I can't go into detail, but such cloud bands actually do need an interaction here between the tropics and mid-latitude frontal systems to appear here over southern Africa. And their appearance or not in a season really is very important if the rains are good in that part of South Africa or not. Okay, so now an even more complicated sketch here from Harvard and Washington here. It's, dividing into austral spring and austral summer. But some of the features you already know. For example, in austral summer here, this is the Angola low. It's a tropical low here over Angola. Yeah, you see the traits, the moisture flux here from the Indian Ocean here. Yeah. There is a heat low here over the Kalahari, Botswana area here. We do have a jet over southern Africa at 700 hectopascal. That's about 3 kilometers here. Yeah. At mid levels, we have a high pressure system and we have a subtropical jet here. These are the players actually of the weather in austral spring and in austral summer. And with these easterlies here and with the jet, there are some tropical disturbances coming from the Indian Ocean here and, resulting in disturbed weather in this part here. So the basic conclusion is moisture is largely coming in from the Indian Ocean. It enters the high plateaus through the valleys of Limpopo and Zambezi. And there are some synoptic systems like the Angola low, like the tropical temperate troughs that are necessary actually to use this moisture for rainfall. Another synoptic feature you may be aware of that brings rain to southern Africa, more so, by the way, to Madagascar, are tropical cyclones that form in the southwest Indian Ocean and that travel westward, that cross Madagascar and the Mozambique Channel and make landfall here, mostly in Mozambique. Actually, most of the tropical cyclones recurve. So they recurve to the south and then west into the mid-latitudes of the southern hemisphere. There are not many that go straight and make landfall in Mozambique, but if, as you know from recent examples, they cause excessive rains, not only in Mozambique, but also in Zimbabwe and Malawi and parts of Zambia, when they stall as remnant tropical lows. Very rarely, actually, these tropical cyclones affect the Republic of South Africa. There's another feature, and now we are actually going to the Northern Hemisphere winter, and we look to the Western Cape region here, and that's called atmospheric rivers. So it's a river of moisture that by synoptic systems, you see here the low pressure system southwest here of Cape Town, and that are persistent and that they cause a moisture stream towards the southern tip of South Africa. And believe it or not, the moisture can actually come from the Amazon forest here. A lot of moisture is then evaporated over the Atlantic Ocean. And for the Southern Cape region, the top 50 daily winter rainfall extremes, 70% were associated with these so-called atmospheric rivers. Now I'm going away from discussing the synoptic system. I go to what is called teleconnections. And I think most of you will be heard of it. For example, the El Nino Southern Oscillation. So this is a figure from the last IPCC report. I have encircled South Africa here, South Africa rainfall. And when you follow these, lines here, this is the Southern Anliar Mode, Indian Ocean Dipole, and so you see the connection to the rainfall here, in South Africa here. And we know that these are important players, but I will detail it somewhat because the IOD here is not so important for South Africa, but the ENSO event and the SIM and also the subtropical Indian Ocean Dipole. Maybe you have heard in the media already, so the forecast for this austral spring and this austral summer coming is that we might have a strong El Nino, which increases the odds of a very dry next rainy season in large parts of southern Africa. Okay, so now the teleconnections associated with El Nino Southern Oscillation. So what you see here is, let me just close this here. Wait a minute, I have to close a window here. Yeah, okay. So here in the top left, you see the sea surface temperature variations associated with a typical El Nino. Here, this region in the Pacific here is the so-called Nino 3.4 region. Usually an SST index from that region is taken to describe the El Nino. And you see here the time series of such an index here. You see Nino 3.4. This is this box here. And we had very strong El Ninos here in 82, 83, 96, 97, and in 2015, 16. And now, of course, there is another strong El Nino forecasted for next summer in your hemisphere. When you go here to the teleconnections here, in terms of rainfall, you see, first of all, regions where it's wetter and where it's drier. But you have to take care here to the red lines here, which indicate a significant correlation at the 10% level. And what you see here is exactly what you might know here in that region. Southern Africa tends to have significantly drier conditions during a typical El Nino. Yeah? Of course, this gives a possibility of seasonal forecasts. The problem is that there are other actors than El Nino, and so not every El Nino, has the same response over Southern Africa. But a probabilistic forecast, I'm pretty sure, for the next rainy season in your region will likely be below average. So there is a so-called Sarkov consensus seasonal forecast that will be issued this winter or this spring in your hemisphere. and it will likely, point to below average rainfall. There is more rainfall in some parts here, like Tanzania, Kenya, to be expected for next austral summer. This is a map of the typical teleconnections associated with El Nino and La Nina here. This is the El Nino and rainfall teleconnection, and that's what I told you in winter here. Our winter, your summer, I have to be careful. You have drier conditions, you have wetter conditions here. And what I'm indicating, there is a so-called of a zero line. And it's, differs a lot between different El Niños, where this line is located, where the, signal goes from wet to dry. And I told you there is, also different flavors of El Niño. This is a La Nina condition here, which we had the last 3 years. In principle, it's wetter, but you see here when you look to the patterns, they are not always symmetric in the sense that, when you go to La Nina, this same area is dry and this same area is wet. There is a difference. And there's also some dispute in our community if the signal here from the Pacific is communicated in the tropical channel via tropical Walker circulations or via mid-latitude westerly storm tracks. And so there is a lot of unknowns. And I want you to know that when you hear these forecasts, it is still a lot of uncertainty that comes with it. Next, I'm going to the subtropical Indian Ocean dipole here. You see here on the top left, the sea surface temperature anomalies associated with a positive subtropical Indian Ocean dipole. So you see warmer water temperatures southeast of Madagascar, and it's colder in this part. Basically, it is associated with a strengthening of the subtropical anticyclone in that region. So an anticyclone in the southern hemisphere is rotating like this. So you have stronger trade winds here. The stronger trade winds evaporate more ocean water, and evaporation means cooling. So that cools this part, and here it is warmer. Yeah, and it peaks in austral summer. So when we have warm waters here, and that's shown here, that's an idealist experiment by Chris Reason here, that, that enhances here this a low pressure system here in that part. Yeah? And that brings in more moisture here to the eastern part of South Africa. So keep in mind, a positive SIOD here brings more rain to large parts of Southern Africa. And this SIOD is not strictly coupled to El Nino. So imagine, if you have an El Nino, your forecast would be for below rainfalls, but there is a positive SIOD occurring. Who wins the game? And I just wanted to tell you, ENSO and its teleconnections have flavors. And if any, a ocean atmosphere coupled model should forecast the SIOD to get the teleconnection to South Africa right. Okay, so now there is another mode that is important. This is a southern annular mode, abbreviated SAM in austral winter, so that's December, January, February. Basically, what it describes is if the stormy zone around Antarctica is more in a southerly position, more contracted to Antarctica, so it's of course a westerly here flow around it, or if it's, going farther, let's say equatorward. If it's positive, it's more contracted, we have more rains in Southern Africa, and that's because of its influence to the Mascarene anticyclone. Yeah? And you see here that correlation, positive and positive means green here, and especially here in that region where my cursor is, we do see more rains. There are two other players. That is here the Indian Ocean basin mode. You see here outlined here the basin mode. So actually it tells you if the entire tropical Indian Ocean is warmer or colder. This time series here is detrended because the Indian Ocean has warmed in the last 20 to 30 years quite a lot due to anthropogenic warming. And this here tentatively leads to drier conditions in Southern Africa. However, it's not significant at the 10% level in this analysis here. So one has to be a little cautious. Nonetheless, because the Indian Ocean is warming, that has been attributed to drier conditions that have been observed recently in Southern Africa, at least in some parts. But I personally would say the Indian Ocean basin mode teleconnection is uncertain. Now I'm coming to the last teleconnection. Oh, sorry, in the Indian Ocean. That's the Indian Ocean dipole mode. And when you look here, you see Western Indian Ocean, Eastern Indian Ocean, west of Sumatra. And we have warmer conditions here, colder here, if the dipole is positive. When you look here to the rainfalls, it's mostly bringing more rains in equatorial East Africa, not so much in your region. By the way, in 2019, we had a record-breaking positive IOD, and in October, November, we had partly catastrophic rains in Eastern Africa. So the impact on Southern Africa is not clear or sometimes conflicting. When we go to the Atlantic Ocean, there is one variations of sea surface temperature to mention. It's called Atlantic and Benguela Nino. So here, usually you have cold waters in the mean, but during Atlantic Nino, warmer than average waters, are here observed in region 3 at the equator, south or West Africa. The Benguela Nino is called here when the waters are high here in region number 1. Very often they occur at the same time. So there are arguments by some scientists that say we should not distinguish between Atlantic and Benguela Niños, just calling them Atlantic Niño or Benguela Niño. And there's a work by Lutz et al. Here on the impact of rains on the West African coast here. So region number 1 is here, Western Cape region, 2 is in southern Namibia, 3 is between northern Namibia, southern Angola, and 4 is in northern Angola. And what you see here is Atlantic 1 is this region, Atlantic 2 is this region, Atlantic 3 is this region. And let's have a look here into this here. 1, 2, 3, 4 means this region, the region 2, the region 3, and the region 4. And not surprisingly, this region here, when it's warmer at Benguela Nino, we do have more rains here. The reddish colors indicate that here. I will not discuss the numbers in the squares here, but you see here the strength of the correlation here with the red colors. So, for example, here this encircled square means we have more rainfall here when it's warm at the same time here at the coast in northwestern Angola. For the northern Namibia, southern Angola, there is not much of an influence here. Also for southern Namibia, and Atlantic Nino tends to have a little more rain here, especially in winter at the Cape region. But, take as a message here that the strong signal here is, of course, in northern Angola. So this is my first summary for you here. So we have looked into large-scale modes of climate variability in El Niño Southern Oscillation, the subtropical Indian Ocean dipole, the Indian Ocean Bathon mode. And these modes of climate variability change the locations and intensities of the subtropical high pressure cell, the winds and evaporation, and thus the moisture transport onto the southern African subcontinent. Yeah? And the most important moisture source for the rains in southern Africa is the Indian Ocean, and the bulk of the moisture flows onto the highland through the valleys of the Limpopo and Zambezi and so-called nighttime low-level jets. Another moisture source is the Atlantic Ocean and partly the Congo rainforest zone, especially for northern Angola and northern Zambia. Yeah? In spring, actually, these Atlantic moisture and the one that comes from the Indian Ocean form the Congo air boundary, which is also an important synoptic system. I mentioned synoptic systems, Angola low, Mozambique trough, tropical cyclones, and so forth. So they are actually using up the moisture. Yeah? If the large-scale modes transport more or less moisture onto the continent, what does it matter? I mean, you need to look to the activity of the synoptic systems that use the moisture. And this variability is yet incompletely understood, and especially at weather, so up to 2 weeks, or subseasonal, up to 1 month, it is not well, known, and it's also hard to forecast. Okay, so I stop here with crash course on what, is causing rains in Southern Africa. And I move on to how actually do we observe changes in rainfall and other parameters relevant for the water cycle. I start again with rainfall. And I want to convey the impression to you that we have a very poor observational basis for the rainfall here. So what are the sources of rainfall? We have surface stations. And the largest source of long-term records are from the stations maintained by the National Weather Services here. Yeah. The problem is often a small fraction of these data is publicly available. Yeah, so the weather services, I know that very much as a researcher having worked in Africa for decades. They are not, giving them to students or to universities or researchers. Unfortunately, you have to pay. There's also a data quality issue, which also depends on the observed parameter. You see here some pictures where you can see that the equipment, even in these first order stations, is often old or somewhat degraded. So I did some work with Sharon Nicholson and Chris Fink, and Sharon Nicholson, she has collected monthly rainfall data for Africa since the beginning of her career. And what I wanted to show you is here, just look at the dots, not at the blue colors. That is the number of monthly rainfall stations she had in the 1930s, 1940s, 50s, and so forth. And when you look into the 2010s here, you see that there are large gaps. They appear here in the 1980s and 1990s here. And, areas, for example, for Congo, we don't have any ground truths. It's the second largest rainforest, and we don't know much of rainfall changes on the ground. Yeah? And if you go to daily data, these maps would look even worse. There are daily data or monthly data available, but you need to, often purchase them. I just give one number here. I don't go into any detail. And so we have a poor network, but also a poor availability of the data for research. This is another point here. That's from a WMO publication, and that's the percentage of surface station reporting to the global surface station network according to the requirements of WMO. And you see the different continents here. The percentage is here. And you see, you know, how Africa performed between about 2011 and 2019. Yeah? Same problem with upper air stations, so weather balloons that we meteorologists need, that weather forecasting needs, yeah, that climate research needs. Unfortunately, it's even degrading here in terms of upper air stations. Okay, if you are, you know, doing a PhD and you need weather data, I have listed here some sources of weather data that are freely available. So here, that's in the US, they collect the weather data that the National Weather Services submit to the global network and archive them. So if you need them, this is a public source. There's another source in the UK here. I actually noted which variables at which time resolution you can get. I will not, you know, discuss this slide any further, but you will get the slides. And if you need surface data, these are the sources. We have to rely in Africa on, let's say, private or non-governmental weather station networks. And one rather famous network is the TAMO network, which has been installed since about 2015 here. There are stations here in the eastern part of South Africa. It's in some nations surprisingly dense. It includes radiation measurements. However, the instruments and the quality varies. You can register for that, and usually for research purposes as an African student, they distribute the data to you. But honestly, I mean, it's a great initiative, but the quality, you know, management of the station is poor. Usually the station from the Weather Service are better maintained. There's also the SASCA network since about 2010. It covers Angola, Zambia, Botswana, Namibia, and South Africa. It's a dense network of automated weather station since 2012, but one has to be honest. When one look into the data, they are also recently start to degrade, so stations go out of operation and they are not refurbished. Okay, so when you work in Africa as a meteorologist or hydrologist and you want to have precipitation as input for your hydrological model, for example, can you actually say, I don't care about these problems and qualities in surface station data. I use satellite data, and can they be used to replace surface observation of rainfall? Okay, here you need to know some key issues of how actually satellite rainfall is estimated here. And one quite famous data set that starts in 2000 is the Global Precipitation Mission IMERGE data set. This data set blends several satellites in the radar, microwave, and infrared wavelength spectrum, and it is calibrated with surface station data where available. Yeah, but you see here, for example, there are a lot of these satellites in the orbit, and I like to show you this next slide. I hope it's working, the animation. Let's see. So I click here. Yeah, I hope you see it. That's a GPM satellite. Yeah, that's the orbit here. There's another, and then you see all the satellites here, and you have to have a mosaic of the satellites to estimate rainfall. Yeah, so it's now faster animated, and then you see the rainfall here in these, you know, yellow, green, reddish shade, and they move across the planet, and you can assess it. But it's indirect, and you have a sampling problem. That is the issue with satellite rainfall estimates. Yeah? And then I told you that there are gauge calibration. There is another product. I give you a listed product later on from the Global Precipitation Climatology Center that's hosted here by the German Weather Service. And they issue, for example, a rainfall product here daily, yeah? And they have an 0.5 degree resolution. And that here is an animation that is Ghana here, how many rainfall stations actually they had per year, yeah, in the different grids. And you see a lot of grids are gray, meaning zero. Yeah, a few have one, and very rarely you have more than one. And so you have to be aware that these gridded satellite rainfall products from stations suffer in regions where we have a very poor, station density. Yeah, so you have to check such products, actually, how many stations enter it to be more, confident of what you are using. There are infrared products. They are based on the geostationary satellites. They have a clear advantage because, you have a time sampling of every 15 minutes. So with these GPM products, you saw the polar orbiters and you have a sample problem. It's also a very high resolution here. And yeah, the rainfall estimation is based on the principle that, deep rainfall clouds in the tropics and subtropics have a cold top here. Yeah, so it's a called cold clouds are measured here. And the famous product often used in research in Africa is chirps. And there are other products here, RFE and Persian. But there is an issue, a problem with the infrared, which I wanted to show you here in iMerge here. So this is a picture over the Pacific Ocean of a rainfall. You see here the caption says millimeters per hour. And this is the picture in the next 30 minutes here. Yeah. So here there was microwave satellite overpassing, but here iMerge had to rely on these cold cloud infrared image. And you see here, this system is, in half an hour, much larger, which is artificial here. Yeah, because the infrared information is used. The problem with the infrared is cold clouds can also be cirrus clouds. These are these high, thin clouds. And there can be, we call it, cirrus contamination. And infrared has problems. So here is a recommendation from me to you regarding if you have to use satellite rainfall products. If you say I need it for the last 20 years, use the GPM iMerge product. There will be a version 7 product to be released later this year. If you need a start earlier in the 1980s, I have also here given you some informations of which products to use. And if you need to start before 1980s, there is no satellite information. You have to rely on rainfall only products. Here I give 2 products, actually, the GPCC product and the Reagan product, which in terms of monthly data, for example, start already in 1891 if you want to use a long-term rainfall record. But be aware here, this is very much dependent on how many rain collectors on the ground were available. Okay, so as hydrologists, you have rainfall, but you also have evaporation. So P minus E or E minus P. So what is actually coming as a freshwater flux from the atmosphere? So how do we observe that? Actually, I can tell you there are very, very poor observational basis for that. You might have seen in a weather station, the WMO has an evaporation pen here. And you can get these potential evaporation data from this ISD website that I announced regarding the rainfall data. But other than that, you have to use here data from satellites. MODIS is estimating precipitation, or GLEAM, which is a combined product using observations and models. Another famous product is ERA5 Land or ERA5. Both are models. Yeah? So in terms of observed evaporation, we largely rely on either models that are forced with rainfall and other data, or here from the MODIS satellite. My recommendation actually would be to use ERA5 or ERA5 Land for evapotranspiration. Now, since you are more on hydrology, what about stream flow? How do we observe stream flow? And I'm sorry about the poor quality here of the leftmost figure here. But there is a river runoff data center that is hosted in Koblenz, Germany here. They have a web page, and you can check, on monthly or daily river flow data. When you look here, actually, the time series end here in parts of South Africa and Namibia are quite recent. But when you go to Angola, it's before 1979 here that stream flow data are available in this database. And I mean, these dots look better than reality. When you go to the page, you will see there are lots of data gaps. So of course, getting stream flow data is another challenge. So here is my conclusion. Often you are interested in looking into extreme rainfall. When you use the smoothed satellite products, they are heavily smoothed, so use station data. That would be my recommendation. If you are interested in trends, also station data are, the way to go. You can use with limitations GPCC, but here changes in the amount of stations that enter the product are important. There's TAMSA Target product. They have a frozen calibration in infrared. Also SHIRPs have been used for trend analysis. Evaporation is particularly hard to assess. And, I would suggest from the sources that I showed you that you use the ensemble mean of all data sets or ERA5. We have few recent runoff data. And I didn't show, but soil moisture and radiation, you need to consult satellite data. Very rarely radiation is measured. I mentioned the TAMO, but TAMO is only available since 2015. Okay, so I just take now what, change do we observe in Southern Africa. After the observed changes, I will make the break and we will come to the climate projections. What is our knowledge? And this is again the paper that I was involved with Sharon Nicholson. And she had, very long-term monthly data here. These are the regions that we considered here. They are numbered by letters here, H and I. H and I are given here. And then I, also copied the region here, M and O, which are here in the eastern part of Southern Africa. What is shown here, that's a, standardized anomaly here of yearly rainfall. Bluish bars indicate above average, long-term average. The red colors indicate below. The green lines here show a long-term linear trend. And you shouldn't be surprised, there isn't a long-term linear trend. So there are fluctuations with drier and wetter episodes. But in that paper, there were few regions in South Africa that had a trend, like a negative trend here in region D, which is the Sahel. So there is no centennial trend here. Of course, you will see later on when you go to sub periods here, there might be a trend. I'm coming to this later on. So this is from the last IPCC report based on the GPCC. I mentioned this data set. Remember, monthly, it started in 1891. But here the trend is given of the annual rainfall here 1901 to 1984. And only where you can see the colors without the crosses, it's a land-only data set because it's based on rain collectors, by the way. You see a few regions like here in West Africa where we have a significant trend. So all over South Africa, there was no long-term trend. When we, take a more recent episode, 1985 to 2014, significant trends appear. For example, actually, and interestingly, here, if you see my cursor here, that's Angola here, southern Angola, parts of northern Namibia. There has been an upward trend. And during the last, let's say, 30 years or so, there has been somewhat of a negative trend here, but it's not significant. Yeah. Keep in mind, all this trend analysis suffers from the data sparseness I alluded to before. And the linear trend, is strongly depending on your start date. Yeah. So if you would change the start date, you might see different patterns. Now to evapotranspiration. So evapotranspiration is evaporation from the ground. It is transpiration from plants, for example. Yeah. So evapotranspiration here is also, of course, since it's actual evapotranspiration, dependent if it rains or not. So this is only based on models. This is a land model intercomparison project that is also a land model here, land surface model that's fed by rainfall. And when you look here, basically the message is that also no significant trend of evapotranspiration. Yeah. When we go to the more recent period, yeah, there is a significantly more evapotranspiration in parts of Southern Africa, but also in the region where it rained more. Yeah. So there is no observational basis of that. That's only model. And increases in evapotranspiration can be driven by increases in precipitation, not solely by increase in temperature or winds. So what are the trends in two measures that are frequently used to describe meteorological droughts, agricultural droughts, or hydrological droughts? So this is the standardized precipitation index. It's 12 months. It's taken over 12 months. And that's the standardized precipitation evaporation index. It takes into account evapotranspiration as a loss. And when we, look into these values here, 1960, 2080, there is no significant trend here over Southern Africa of this too. Only in the eastern part of what is called consecutive dry days. So the number, of dry days during the year has increased significantly. What is the trend in the terrestrial water storage? Actually, we only can do that by satellite that measure more or less the gravitation. If there's more water in the terrestrial, part of the Earth, in the upper part of the Earth, there's more gravity. Yeah? And this is only possible since 2002 because the satellite GRACE has not been in orbit before. Yeah, what we see here is, I mentioned this more rainfall here in parts of southern Angola, northern Namibia, here also in the central part. Yes, there has been more water here in the upper part here in that region, and there is a precipitation decrease here in the recent, let's say, 15 years or so until 2016 here in the eastern part. Okay, so now what has caused this observed changes? We call this attribution to, for example, greenhouse gases or aerosols. actually, this is only done by models. And I have to start a little bit with what type of models do we use? So we use so-called Earth system models. The Earth system models really include the atmosphere, the terrestrial biota here, the land surface hydrology, the ocean. Sometimes, not all of them, include ice sheets. So we have really the atmosphere, the hydrosphere, the cryosphere covered in these models. However, because it's computationally so demanding, yeah, they have a resolution of 100 by 100 kilometer per grid cell. And I just wanted to show you, especially for the tropics and also partly for the subtropics, they cannot resolve the thunder clouds in this square here. So how many clouds do we have? How many rain showers and thunderstorms are in it? Yeah, we can only parameterize it. Yeah, and we cannot explicitly simulate, I'm sorry, the rainfall systems in your area. And this unavoidably leads to problems in the simulation of rains in Africa. So what I'm saying here is models have problems. And, one consequence is here, and this is, allow me here to have one, slide on the climate projection here already. That is the long-term 2080, 2100. And this is the SSP 5 8.5, a very strong scenario here. This is the reference period. And what you see, because the models are not very good, is here that most of the region, we have no change or no robust signal or conflicting signal, except here for the southernmost here, southwesternmost region. Yeah? And this is another, reflection on that here. For example, here are the models here. These are, let's say, 20 models or so. If you go in this direction, you see the changes in each individual model for your area here. And you see here, there are some models which don't, show a change in rainfall. Some show a drying at the end of the century here. And so you have to be really, really cautious with the models here. And here is some, guideline as to use the CMIP6 or Codex model. I will not allude to it, but, take the message here. The attribution of the present changes and the future changes, carries some uncertainties. And what are the sources of other uncertainties in the climate models here? Yeah, for example, this is a work by Hawkins and Sutton, and I just wanted to, draw your attention here to this slide. It's not rainfall, it's the global decadal mean surface air temperature. And that is, we start our climate projections, for example, in 2015 and integrate the model until 2100. That's an example. And the blue here means that's the model uncertainty. Yeah? You see, especially in the next decades, a lot of uncertainty in the climate projections come from the imperfect models. Well, there's always noise in the climate. Climate varies. This is here the orange color here, which goes away. Yeah. And then this green color is the uncertainty in the climate projections due to how much greenhouse gases actually mankind will emit. Yeah? But you see here, imperfect models play a role. So we have these sources of uncertainty. The model physics is not perfect. The atmosphere is a chaotic system. We have the human factor. Okay, so now I think I'm done with 60 minutes here, and it's a good point before I show you the attribution and the climate projection to make a break for 15 minutes. I will stop now the presentation mode and allow you to ask questions before we go into the break. Okay. Yes. So you see, I see the room. So do you have some questions.
Yeah, do we have any questions in the room? Those online, do we have questions?
So if you don't think about questions, there will be another opportunity. There's one in the chat, I think. Yeah. I can't read anything in the chat.
It is an odd, I think, message.
It's an old message. Okay, yeah.
Yes, yes.
Okay.
Any questions? No questions? Okay. Looks like in the room there are no questions.
Okay, good. So I suggest that at 10:45 I resume. Yeah. And until then you can take a comfort break. I will ask again after the break if you have, some questions. Otherwise, I will continue with the attribution and climate projection. Thank you very much. Until then.
Thank you.
So I would continue now. I hope you can hear and see the screen.
Yes, we can hear you, Prof.
Good. Okay. So I stop with, model uncertainties, but now we, go to the attribution of observed changes to forcings of greenhouse and aerosols, plus we will do some climate projections. So what you see here is from the IPCC report again. Here I'm going to the laser pointer. So here you see the so-called fingerprint of greenhouse gases here on changes, recent changes here in rainfall. And that is of aerosols. There is another measure here, aridity. Basically, it is precipitation minus the atmospheric evaporative demand, so a little bit of P minus E. So what you see here is that greenhouse gases tend to enhance rainfall, for example, here in the IDCZ region of the Pacific. They tend to decrease rainfall here in Southwest Africa and in the region here, crossing South Africa, going to the eastern coast of Mozambique, for example. So they tend in the models to decrease rainfall. A typical, increased region are the mid-latitudes cold areas where simply the warmer temperatures lead to more rain. Aerosols, they can be biomass burning aerosols. In your region, they play a large role. They can be dust from deserts or also other emissions from humans. They have a weaker signal, but they have an overall tendency to decrease rainfall. When it comes to aridity here, you see a clearer signal appearing from the greenhouse gases. So in part, the changes, the recent changes in the rainfall, the recent drying which occurred here can be attributed to greenhouse gases. However, we saw that we had recently in the last 40 years more rain over Angola. So there are also regions in which what the models tell us in terms of the greenhouse gas signal is not observed, either because the models are wrong or because another signal, a chaotic signal in the climate system, overrides any greenhouse gas signal. Okay, so now what are the projections of CMIP6 for the water cycle here? There is here the change in rainfall. Here I used the 4.5 scenario, so that's a medium scenario, not the low-end scenario here, but also not the high-end scenario. And this is for the different seasons here. DJF stands for December, January, February, March, April, May, June, July, August, September, October, November. And on all these maps here, you see that if there is a color, it's a high model agreement. And if there is this hatching, there is a low model agreement. Just allow me, by the way, to close the door here. Sorry for that. So we have here in June, July, August, that is, of course, the dry season, except at the Cape region. We have a decreasing trend, but it's already the dry season. The more important wet season here, December, January, February, you see this hatching. So for the light greenish plus and the brownish minus region, which means that until the end of the century, we have a low model agreement that the region will see less rain during the rainy season. I'm talking about total rain. I'm not talking about intensity of rainfalls. That is now the projected change in seasonal mean evapotranspiration here. Here we have only the austral summer rainy season and the austral summer dry season. So there is, because there is less rain, again, it's already the dry season, there is also a decrease in evapotranspiration. But when it goes here to the rainy season in most regions, the exception here is the southwestern corner, we don't have a large model confidence in evapotranspiration either. And that is, of course, related to problems in the certainty with which we can, suggest changes in rainfall. Okay, now I'm coming to soil moisture projections. Again, the same scenario here. Yeah. And this is an annual signal. It's the top 10 centimeters of the soil and the total column of the soil. That depends a little bit on the model, typically about, a few meters just. And what you see here is that there is a drying trend over the whole year in the top 10 centimeter with the strongest signal here in the southern part. So there is at least a model agreement of the drying of the top centimeters of the soils. Now there is the projected change in the seasonal mean runoff, DJF, JJA. And when you look into it here for the rainy season, we do see some projected decrease here in the more western parts of Southern Africa, but there's a low model agreement, whereas a reduction in stream flow during the dry season, there is a larger model agreement. Yeah. Okay, now I'm moving from the mean precipitation to precipitation extremes. Here we have another, representation of the warming. It's called the global warming levels. Yeah, models have a different sensitivity to greenhouse gases. And so here we look into the models when the global mean surface temperature has exceeded 1 degree, 1.5. Remember, that is one of the Paris Agreement here, 2.5, 3.5, 3.0 and 4.0. Yeah? So this is, of course, a strong warming. And when we consider these maps here, this is here on the y-axis, the number of times as frequent as now, if you wish. And this is a 50-year precipitation event, and this is a 10-year event. And this slide here, for example, or this figure here, for the strongest warming, the 50-year event, that occurs now will be more than 4 times as likely occurring at the end of the century. So when we look now into Western Southern Africa, the eastern parts, so the basic, message here is that there is an increase, with the warming levels in the return periods of the 10 and 15-year events, more so of the infrequent 50-year events. And the basic message here that you can take from it, models agree, that's, by the way, the range of the models in the Bos and Wiska plots, models agree that if it rains, it will be more intense. That has something to do with the warmer world and the fact that the warmer atmosphere can hold more moisture. Often we call that the Clausius-Clapeyron scaling. Yeah. So now there is a table here, and that's, by the way, the chapter 11, led by Sonja Seneviratne here. That is fidelity of the assessed changes for your region, the western part, the eastern part. I mean, I'm not talking about hot extremes because we are dealing with the water cycle, but you see here in observations in the attribution that we do recently, that is here the warming levels, that the baseline is pre-industrial before 1850. The baseline is now that we have, a likely and very high, confidence that it gets warmer. But let's look into heavy precipitation that I mentioned. So there is medium confidence already that heavy precipitation has increased in the observations in your region already. Where it comes from, does it come from, greenhouse gases, aerosols? We have low confidence because of the, problems in the quality of the model. So now we move on to the changes in 1.5, 2, and 4 degrees warmer world with respect to the pre-industrial. And, we see here the low confidence in the 1.5, but when it comes, to the higher warming levels here, medium confidence, likely here, this is a likely change, yeah, that heavy precipitation will indeed, increase. That is a different baseline. I don't want to discuss this here anymore. Then there is a line, agricultural and ecological drought here, and there's hydrological drought. And you see here, when it comes to observations here, we have a median confidence here that, we do see more of these agricultural drought already. We cannot attribute it, with any confidence to the climate warming now because of the climate models. They are imperfect, but I also mentioned the chaotic behavior in the models. For the hydrological droughts, it's even, a lower confidence. When it comes to the climate projections here, you see that, especially agriculture droughts becomes increasingly likely at 4 degrees. We have a high confidence of an increase here in the 2 degrees. Yeah, but hydrological drought, the factors are lesser. When you compare here the western part with the eastern part, you see here we do have some higher confidence in the changes of heavy precipitation in the already wet eastern part of your region. So that is definitely a difference. So the basic line is we do see with medium confidence an increase in precipitation and also with ecological drought, and this situation will worsen with higher global warming levels. Okay, so I also copied these box here, also from the IPCC report, and in the brownish color, show you regions in which drought, remember we already saw a significant increase in consecutive dry days in your region. So the drought will, increase regardless of the future warming. If we have 1.5 or 2 or 4, this region will see, an increase in drought, not necessarily a drier mean annual rainfall. Yeah? That has to be, distinguished here. So, we are about in the next, let's say 5, maybe 10 years to have, average temperatures above 1.5. So we are, starting to cross the 1.5 level in the coming decades, which also means you should be better prepared for future droughts in your region. There's another issue worthy of mention here. That is the changes in the river discharge and the shoreline here. This is a change in the 1 in 100-year river discharge per unit catchment by mid-century in the strong here scenario codex is with regional models here. Yeah, and you see an increase in cubic meter per second per square kilometers in many rivers here in eastern South Africa, as you can see here. Another concern is the shoreline position, because of the sea level rise, you see here the dots, a retreat in the shoreline. What does it mean for your region, especially in the eastern part? So Mozambique, perhaps the northern part of the Indian Ocean coast of the Republic of South Africa. Yeah, they will see a higher discharge in rivers, and at the flat coast, they will meet the higher sea level. And especially when tropical cyclones make landfall, we will see more extreme coastal flooding. Two factors: the landfalling cyclones, sorry, three factors: the higher discharge and the higher sea level. Okay, so that is a summary here, and actually that is also my summary slide. Here we have no long-term trends in mean rainfall or evaporation in your region. When I say long-term, I mean in the last 100 years. Yet, of course, in recent years, observational uncertainties remain because of the poor coverage of the region with rain collectors. What we do see is a trend towards more consecutive dry days, so a trend towards also drought conditions. Yeah? And what I have not listed here with medium confidence, when it rains more intense. Yeah? The projected changes in mean annual rainfall in your region, yeah, and also therefore evapotranspiration changes remain uncertain due to model deficiencies here. Yeah? So when somebody tells you, oh, it's going to be drier, it's not drier in terms of the mean annual rainfall. It's drier in terms of spells where it does not rain. Yeah? We have high confidence in the changes of variability, for example, more intense precipitation and higher drought frequency. And this will definitely translate into more extreme hydrological and agricultural droughts, yeah, as well as higher peak discharges and coastal flooding in eastern South Africa. So you are the first cohort of the, SGSP on integrated water resource management, and you are the generation that needs to work on adaptation and mitigation measures to these anticipated extremes in the water cycle. And what my, message here is, we do see the changes in your region already. So we need to implement them ideally now or in the very near future and not at the end of the century. Yes, so actually, that is my last slide. You will get also some of the references I, cited here. And I would say and hope that we could have a discussion. You could have, questions, but you could also, make observations like, I do see the drought, or I don't understand this at all because I have considered in my region or seen in my region an increase. So please feel free to ask questions now. Also in the chat.
Thank you, Prof, for that wonderful presentation or lecture. Please, anyone with a question, those online, those in the room, any comment? I think we have a hand here in the room. I think you need to move closer.
Yeah, just come closer.
Come closer to the mic. When you speak that side, it's very hard for him to. Just come closer here and ask your question. Yeah, come here. Stand here so that you can see you. Yes.
Good morning, Prof.
Good morning.
So my question is, according your understanding, this every change is because of the human change or human cause? Natural cause. Natural cause.
So can you repeat your question? So you were talking about human or natural cause? I didn't get it.
Yeah, I want to know because, for example, when the Prof show the change about the monster and the water in Angola, Namibia, South Africa, I had one question. My question is, this change is motivated mostly because the human change or natural change?
Okay.
Sorry, my English is from
No,
United
I
States.
got you. Your English is very good. Thank you very much. And thank you for your courage to ask, even though my answer might disappoint you somewhat. So, yes, we have seen an increase in rainfall in the last 40 years in some parts of Angola. Yeah. And I told you that the models are very, doing a poor job. My personal opinion is that what we see is natural. It's not anthropogenic, because the anthropogenic signal, at least according to the model, would tend to reduce the rainfall in Angola. So what, the reason for this increase in rain in Angola is, I cannot answer. It should have something to do with changes in these teleconnections that I mentioned. So changes in the water temperatures, Atlantic Ocean, likely. So maybe off the coast of Namibia and Angola in the Benguela Current, or some changes in the Indian Ocean. The basic, understanding of me is that we should consider this change being natural. I hope that answers your question. Thank you.
Another question, Sydney.
Please don't be shy. Good morning.
No, Prof. Good morning. My question is just want to get your recommendations on the Southern Africa region. Which are regional climate models we can use in our study for climate change in the region? The one I'm asking for your recommendations. Which ones will be perfect for our studies?
Okay. Thank you very
Thank
much
you.
for that question. So, perfect model for the region, it depends on the purpose. And then, of course, each model has a certain, set of parameterizations, for example, of rainfall, of convection. Yeah. So it's also the question which model actually you can get for free. Many models are now available for free. Here is my personal view, and others, my colleagues, might disagree. Yeah, but I prefer the weather research and forecasting model WRF from the US. Why? Because you can use, a lot of different parameterization methods. Of course, this leaves you with the problem which of the configurations to use. And what I'm doing is, there is lots of literature on WRF. I would go to literature, check for South Africa or the tropics which configuration they used, and then use WRF. Yeah? A second model that is often used is the one from Trieste in Italy. It's called RECCM. So I have seen also good results of RECCM. So first WRF, second RECCM. WRF, as you know, is relatively easy to apply, has a lot of options, but of course the options for parameterizations, and I can tell you for your region, for example, parameterization of convection matters a lot. You would need to go to previous literature and try to use what they have used. More questions, please. Also
Another
online.
person is coming.
Okay. Morning, Prof.
Morning.
Yes, thank you so much for the presentation on climate change. I just wanted to get an opinion from your side. I made to understand that there was a delegation that came to Bonn, Germany to have a kind of a review of the Paris Agreement on limiting the temperature to a maximum of 2 degrees and keeping to the low of 1.5. But the consideration of the team is the fact that even the 1.5 limit is actually not even viable now. So the consideration is the fact that maybe we should bring down or something like that. So I wanted to hear, Prof, if you are privy to that meeting and what do you say about that current, I think it took place early this month in Bonn,
Okay.
Germany. Thank you, Prof.
So I don't know about this meeting, but I can say something on your point here, because I was also interviewed here in Germany in the media, because, you know, there was a recent report of the World Meteorological Organization on what to expect in terms of temperatures in the next 5 years. And, you know, there is actually a chance of more than 30% that we already exceed 1.5 in the next 5 years. Yeah. And when you see the emissions and the plans of the nations, my personal opinion is we should not talk about the 1.5 degree goal anymore. The more realistic goal is 2.0. But that's the opinion of a scientist. And if WMO is a political organization, and that means, you know, they have not given up that goal. But my personal opinion is it's unrealistic. So the global warming level of 1.5 we will experience already in the next 10 to 20 years. That's what I can say. Thank you. Good question. More questions?
Okay. Another question. Someone's coming.
Thank you, Prof, for your insights on the previous question, and also for the presentation that you gave on climate change. Mine would be also more of a practical question from yourself as a scientist, looking at the research policy implementation interface. Where would you say that we're missing it out from yourself as a scientist? And this in particular, it's also looking at, yes, you showed us the climate models, the different models, and it's actually quite at a global scale, as it were. And it's also quite a coarse, I feel, it's quite coarse in terms of spatial and temporal sort of resolution, because you're looking at five year or even longer terms. And yet, when it comes to policy, and we're looking at policy makers, they usually have a political cycle. So, what is the relationship currently between downscaling, what you're doing at that global and international level, to inform real-time policy making, so that we can start to maybe talk about the 1.5 to 2 degrees Celsius within this generation? So where is the gap here between science informing policy in this day and age? I know it's a bit of a convoluted statement, but yeah, why I'm asking that is because my research is looking at the water, energy, food nexus, and I'm also looking at smallholder farmers and what they can do to adjust and build their resilience to climate change. So for me, the smallholder farmer is more interested about the rainy season, the next rainy season, not what will happen in 5 years' time. More interested in the drought that we're projecting for the next year, not like the 25 to 30 years time that will come. So yeah, there's a bit of a mismatch there. So it's quite interesting, and I'll be interested to hear what you have to say about that gap. Where are we missing the link?
Yeah.
Thank you.
So thank you very much. I mean, there's no easy answer to your question. As you said, it's a somewhat convoluted question, but I want to pick up one point that you made. let's say, lead time horizon of interest for farmers, as you said, is the next rainy season, a few months. And we are here currently trying to get a project running in Southern Africa, funded by the German government and with participation of researchers and institutions in Southern Africa, including SASCAL, where we want to improve on what we called hydrometeorological forecasting from 2 weeks out to 7 months. Yeah. So I mentioned in my talk early this El Nino thing. Yeah. So actually, one point is there is a so-called SARCOF. It's a so-called Southern African, consensus forecast that is made by SADC CSC in Gaborone before each rainy season. But, it's very coarse. It just gives some tercile probabilities of above median or below average rainfall. It's not, it doesn't have any temporal resolution rather than 3 months. And what we want to do is to improve these information for dam managers, for smallholders on the rains in the coming weeks and months, because our belief here is we do see the impacts of climate change in Southern Africa already in terms of longer drought spells and in more intense rainfall. And I think, like here in Germany, to make people act to reduce greenhouse gas emissions also needs to raise their awareness that they are already living in times of climate change. Here in Germany, we have seen unprecedented droughts in summer. We have seen unprecedented, heat waves. And so now the population here, they don't, question, most of them, that climate change is real. Yeah. But we need the tools and the measures to, improve preparedness now and not so much at the end of the century, because this time horizon may be interesting for, let's say, wine farmers, for some dam managers, but not for most of the people. That is the answer. It will not answer your question totally, but I agree with you. Climate change is real, and we need to develop tools to, mitigate the effects now. And one of the tools is better forecast for farmers. And we are working on it. Thank you. More questions, also of practical,
I see no one with a hand in the room. I'm not sure about those who are online. Any question from those online before we close? I see no one, Prof.
Okay. Yeah. So let me just say, if you have some questions, practical issues where you think I could be of help, just email me. I'm happy to help. I have some exciting classes throughout the week. I know my distinguished colleagues will give, classes on topics that you are more used to. But of course, climate and climate change is the driver of the changes we see on the ground. And yeah, you are the generation, I think, that is, not only feeling the change, but should develop tools to adapt and mitigate. Thank you very much.
No, thank you so much, Prof. Can we just yeah. So just for those online, we are continuing next tomorrow. Actually, we have a class from 9 to 12 as well. So we'll have other speakers coming through. I think the same speakers on Tuesday and Wednesday. Right. So please join us tomorrow. You can use the same link that we have shared that you used today. So thank you so much for joining us.
Yeah, just one word. There was a question in the chat, can we have the slides? I would send PDF copy of the slide to you. So, and feel free to distribute them amongst the students, please.
Okay, so for those who are online, please, we may not have your email addresses. Just drop them in the chat box. When we get the presentation, we can circulate to everyone. I see Rennie's hand is up. Please, Rennie, come through.
Thank you. Thank you so much, Prof. Thank you, Dr. Moore. I just wanted to appreciate your time, Prof, and just to also request if there are additional resources or even opportunities that can grow the knowledge of our students, even post this Common IWM course, would really appreciate if you can share it with us. Then we'll further circulate it to our students, because the thirst to learn is quite huge, not just for the students, but also Secretariat. So thank you so much for your support.
Okay, thank you, Rennie. And all the best to you and all. Okay, bye.
Thank you.
Thank you.
Bye.
Bye.